Thank you, and I'd like to thank the organizers for inviting me to speak at this workshop, which has been really stimulating. This work that I'll be telling you about has been done largely in conjunction with Steve Tobias, who you heard from yesterday, and who did a great job sort of setting the stage for what I'll tell you about today. A number of the things I'll be mentioning are in this recent review article, but I'll be telling you about a number of other things that we've discovered since then. And there's been a large number of collaborators on this project over the years. So Steve took all the hard questions yesterday, so I'm prepared to field the easy ones. And as you'll see, we have many questions. So maybe as a sign of a healthy field, this subject continues to surprise me. So let me just begin a little bit with the motivation, which is that most of the turbulent flows we see in nature are highly anisotropic and inhomogeneous. So here's a visualization due to fog of the wakes of some wind turbines, offshore wind turbines, which I'm going to actually return to at the end of the talk. And the kind of engineering approach to understanding such flows might begin with direct numerical simulation of Navier-Stokes or some modification, and then realizing that we can't possibly simulate such a system on an existing computer, so we maybe do a large eddy simulation, and maybe that's even too expensive, so we would do some further reduction of the problem with some averaging. And I'd like to take a different point of view, which is really to begin with the questions that we seek from a description of turbulence and focus on the statistics of turbulence, since, of course, any one realization of turbulence, given its chaotic nature, isn't so informative. But we'll be focusing primarily today on low-order statistics of the turbulent flow, but we'll also look a little bit at some high-order behavior. So as an overview of where we're going, we're going to be looking at a number of non-local closures, so different than the sorts of closures that are usually considered for turbulent flows, such as an LES. And so I want to contrast the numerical simulation approach with what we call direct statistical simulation, which is to solve directly for the statistics of the flow. And to categorize this by increasing degrees of triad decimation, such as Steve mentioned yesterday. So Steve told us about how one could go from the fully nonlinear simulation to the generalized quasi-linear simulation, and then further reduce to the quasi-linear simulation, where the mean flow is just completely, has no wave number. It's steady in at least one direction. And I want to tell you about the corresponding closures for these types of approximations. The most extreme of which is the second order closure that we call CE2, because there's two cumulates, and has also been called stochastic structural stability theory by Farrell and Ianu. Even though this has actually been around for a long time, as we'll see, it still has some surprises for us. Now, a lot of these systems I'll be telling you about fit into the anti-diffusion theme. And we heard a talk on Monday by Nicholas looking at the jet formation due to stochastically stirred barotropic fluid on a rotating sphere, beta plane. And so that's a really sharp example of anti-diffusion. But it also exists in deterministic systems. So point jet problem that we looked at the start of this adventure, one of the first things we did was calculate the eddy diffusivity and show that it is negative in certain regions, concentrating the jet more than you would expect from a diffusive closure. So just to review, again, the quasi-linear approach, which goes back at least as far as Malchus, and maybe even further back. I suspect that Malthus was perhaps motivated by Hartree-Fock approximations, a mean field theory that his advisor Enrico Fermi surely worked on. And we'll look at a dynamical system with some linear term and some nonlinearity, but we'll only consider quadratic nonlinearities. And an open question really is how to deal with higher order nonlinearities, such as step function nonlinearity from latent heat release. And so a prototypical problem that we've already seen many times here would be this barotropic flow, perhaps stochastically stirred with some hyperviscosity or some friction, but we'll be looking at other types of models too. And we need to think about different types of averaging operations. So, for example, if we were to look at a cloud-topped boundary layer, we might be interested in a horizontal average, horizontal spatial average, because it's rather homogeneous statistically in the two horizontal directions, but certainly not in the vertical direction. But we might also consider ensemble averages, time averages, and so on. So I won't have much to say today about ensemble averaging. It's very interesting, but it's computationally intensive. So I'll be focusing on zonal or spatial averaging. And Loretta has looked at a time averaging approach, which is interesting too. So we decompose our dynamical variables into a mean plus a variance. And then, as Steve discussed yesterday, write down equations for the mean and the fluctuations, where this last term is this so-called pain in the neck term that we drop in a quasi-linear approximation, but we may wish to retain it for higher order treatments of the problem. I like to view this in terms of triadic diagrams. So the first diagram here shows a wave that is scattering off of the mean flow. So the wave number here is, say, labeling the wave number in the zonal direction, the direction that we're averaging. And so we have this zonal mean flow that has 0 wave number. So this term is what would be present just in a linearized treatment of the flow that doesn't attempt to self-consistently adjust the mean flow. But if we retain the term that involves the forcing of the mean flow by the eddies, then we have this set of two equations, the quasi-linear equations, that are self-consistent mean field theory. But that neglects this general term in which two waves scatter into a third wave. So Steve discussed Kubo number and other ways of thinking about asymptotic limits of these equations where we might expect them to be reliable, that is the quasi-linear approximation. And one involves large timescale separation between rapidly fluctuating eddies and a slowly evolving mean flow. Alternatively, we could just dampen the waves by some mechanism, maybe a lot of friction, to suppress their amplitude compared to the mean flow. And since this is a kind of perturbation in the strength of the waves, this can lead to a reliable approximation. And there's also a kind of pathological limit in which we just drive a single wave vector, and therefore this triadic interaction may disappear unless there's some sort of secondary instability. Now, so I want to emphasize in this talk some open questions. And one of the open questions is the presence of what we call an infinite U1 symmetry in the quasi-linear equations. And what that means is that if we just retain these two diagrams, we can rotate the phase of any wave by an arbitrary amount at each zonal wave number. And that cancels out, or it just passes through this diagram. Here, the wave, the phase, we'd have e to the I theta and e to the minus I theta for the two waves. And so these equations are invariant under an infinite U1 symmetry. So the equations of motion have this kind of symmetry, which is not present if we have the general triadic interaction, because it mixes all the different wave vectors together. Now, if we just do a linearized approximation, I get rid of the forcing of the mean flow, then we know how to write down a Hamiltonian or a Lagrangian version of this linear theory and apply Noether's theorem to it to find the conserved charges, the conserved currents, which are the pseudomomenta. And so on the sphere, they have this form, and for each zonal wave number, we have this conserved quantity in the idealized limit where we turn off damping and driving forces. But the symmetry is there also for the quasi-linear theory, and we have been unable to write down a Hamiltonian or Lagrangian description. And perhaps somebody here knows how to do this, could help us do this. But absent that, we don't have a way of constructing a conserved charge, and perhaps it doesn't exist in the quasi-linear theory. But if it did, it would be extremely valuable, because then we would have a conserved quantity at each zonal wave number for the quasi-linear theory. So if we just do a numerical simulation, we can compare linear, quasi-linear, and fully nonlinear conservation of pseudomomenta. The black line here is just steady with time. This is for some barotropic model. And you can see the quasi-linear, if I just do a quasi-linear approximation but adopt the linear definition of the pseudomomenta, it is better conserved than the fully nonlinear simulation. So showing that the quasi-linear theory doesn't have as much scattering in it, and so this is perhaps not surprising. But what's not been emphasized in the literature very much is that actually the pseudomomenta is conserved at each zonal wave number in the linear theory. So there's an infinite number of conserved quantities, infinite U1 symmetry. Now, condensed matter physics may offer some ideas about how to approach this, because we're always dealing with a Hamiltonian there. And in the case of a metal, we have Landau Fermi liquid, which has an emergent infinite U1 symmetry, which is reflected in the infinite lifetime of quasi-particle excitations close to the Fermi surface due to something called Pauli blocking. Yes?
Very trivial question. This graph is supposed to show the conservation of each individual pseudomomenta for each zonal wave number?
Yes.
But those curves look as though they're changing.
Well, so focus on the dark line. So this is the linear theory. So this is in a linear simulation. And this is the m equals 5 pseudomomentum, and this is the m equals 3. The colored ones are for the quasi-linear or nonlinear simulations.
Okay.
Thank you. Liquid helium has a description in terms of something called Bogoliubov phonons, which have an infinite lifetime. And in the usual approximation that people treat this, the simplest approximation, it's kind of like the linear theory. But if we allow the, and we find this infinite symmetry, this infinitely long phonon lifetime, they don't scatter. But if we allow the condensate, so this is a little bucket holding liquid helium, or an experiment showing its superfluid properties, then the condensate will adjust. That's like our quasi-linear theory. And, but we've been unable to find the conserved quantities in this case either. Although we're continuing to work on it, because we think if we could do that, we might have some insight on how to approach the classical fluid problem. So now I want to discuss the cumulant expansion to second order. And this really goes back to an observation that Jack Herring made in 1963. When he said that discarding of the fluctuating self-interaction then corresponds to closing the system of moment equations by discarding the third order cumulants. So he realized that this quasi-linear approximation allowed you to have an exact closure at second order. And Jack passed away a couple years ago. I was fortunate I was able to have a conversation with him about the history of quasi-linear theory a few years ago. So if we don't discard the general eddy-eddy to eddy interaction, then we have the famous hierarchy of cumulant problems. So the first cumulant is coupled to the second cumulant is coupled to the third cumulant, and so on. It's turtles all the way down. But if we have a quasi-linear approximation, it just truncates at two turtles, the first and second cumulant. That's what Herring's saying. So I'll write the first cumulant as the average of our dynamical variable, and our second cumulant as the average of the fluctuations of our dynamical variable. And again, we're just retaining these two types of triadic interactions. And now we can write down the equations of motion for these cumulants. So the tendency of the first cumulant involves a linear operator acting on the first cumulant, plus the nonlinear operator acting on the pair of first cumulants, plus the forcing from the second cumulant. This is this Reynolds forcing of the mean flow acting through the nonlinearity back on the first cumulant. And then the tendency of the second cumulant involves a linear operator that depends on the first cumulant. So that's the linearization about mean flow acting on the second cumulant. And then there's also feedback. So it's the same term here. So it's basically the scattering of the second cumulant off of the first cumulant. And we've truncated, we no longer have any coupling between the second cumulant and the third cumulant because of this quasi-linear approximation. But importantly, it does not mean that the third cumulant vanishes, which was a misunderstanding that I had for many years. So in the concrete case of zonal means on a sphere, what that means is that our first cumulant, we just look at if we do a decomposition in terms of spherical harmonics, we have only the m equals 0 spherical harmonic amplitude here. And the second cumulant involves a product of our dynamical fields decomposed in this Fourier space, where we have the two fields are at the same zonal wave number, but because there's a complex conjugate, you can think of this as having 0 net zonal wave number, and therefore it survives a zonal average. Now, here I wanted to discuss a recent surprise that we had, which is that even though those equations are derived exactly from the quasi-linear equations, they don't necessarily have the same solution. And this was pointed out to us by Rich Kurzweil. So we can illustrate the problem by just looking at a very simple linear problem, where we have two decoupled ordinary differential equations. So the tendency of x is 2x, and the tendency of y is minus y. So we have one unstable direction and one stable direction. So we form the second cumulant by taking a snapshot of this behavior, and I've dropped the primes here just for simplicity. Then I just multiply a row by a column vector to get this second cumulant. And this second cumulant has only one non-zero eigenvalue. It's simply xy, because this is just a projection onto the eigenvector xy. And it has an eigenvalue of x squared plus y squared. There's another eigenvector which is orthogonal to it, which has eigenvalue 0. So the rank of this matrix is just 1. There's only one non-zero eigenvalue. But if I do the solution, if I find the equations of motion for the second cumulant, directly using these equations and then multiplying by x, so I'd have the time derivative of x prime squared, then we have 3 such equations, and there are now 2 unstable directions. So the rank of the second cumulant, as determined by this solving for the second cumulant directly, from the direct statistical approach, has rank 2 and not rank 1, as it did from the snapshot over here. So this has profound implications when we're comparing quasi-linear simulations and the direct statistical simulations. And I want to now tempt fate by doing a live simulation for you of this phenomena. So what we're going to be doing is we're going to be solving the barotropic vorticity equation forced by this Kolmogorov type forcing involving the second and eighth associated Legendre polynomials. So in the sort of latitudinal direction. So let's see how this works. So first we're going to do relatively weak forcing. So the amplitude of this Kolmogorov forcing is going to be weak, and we'll go up and solve the quasi-linear equations of motion. So this mesh that's being built up on a sphere here is just for the purpose of visualization at this point, because I'm actually doing the calculation in spectral space. So if I run this, we can see some instabilities immediately develop, and there's some pretty rich behavior that's evident. And if we look at it in spectral space, then what we see is that only the first three values of M are excited. And so this is a plot of the power, whoops, this one. In spectral space, this is the zonal wave number M. This is the spherical wave number L. And so M equals 0, this is the mean flow down here. And then up above, we have M equals 1 and M equals 2. There's two waves in this system. And I'd like to actually do that again, because I want to do some time averaging here to accumulate the average energy in the system. So let's look again at the power spectrum, and then I'll turn on time average. Let that go. All right, so now if we go down to our results here, we see that the average kinetic energy is equal to 0.0681 here, I think. No, it's this first one, 0.0639. Let me erase that bottom one there. And now let's repeat this calculation using a second order cumulant expansion. So now we only see the zonal mean, because that's what's being displayed here. That's the first cumulant. And if we look at it spectrally, we again see the same wave vectors are being populated. And I'll turn on time average. Notice, by the way, that this does not flow to a fixed point. And that's what we typically find with these second order cumulant expansion, is that it continues to oscillate. And the spectrum is exactly the same as for our quasi-linear simulation, and the energy is exactly the same. So this is a perfect agreement between the quasi-linear and the second order cumulant expansion. So now I'd like to repeat this experiment with the strong forcing. And again, we'll do the quasi-linear simulation. And we see all the instabilities, rather interesting behavior. It'll slowly turn over on its side here. Let's visualize this for a bit, and then we'll look at the spectra. Okay, so let's look at the power spectrum. So now we see that due to the stronger forcing, we're actually getting some amplitude for the third M equals 3 mode. And if I time average, we can accumulate this spectrum. And so maybe it's not surprising that we have this, due to the stronger forcing, we've introduced more instability into the system, so there's more waves. So finally, let me look at this in a second order cumulant expansion. So exactly the same problem. And we'll look at the power spectrum. So at first, we have all of the waves presenting themselves. But now, as the system settles down into a statistical steady state, we no longer have any power in the M equals 3 mode. So, and the reason for that is that the second cumulant now, the non-zero entries in the second cumulant now are greater than rank 1. And so that means that there's more channels for energy to go into those other non-zero eigenvalues, depleting the M equals 3 wave from being excited. And if we look at the total energy, let's do a time average, is now going to be different between the two results. It's actually, you can see here, the first two entries down here are the weak forcing where the total kinetic energy agreed. Now we have very much different results. The reason I emphasize this is that there's been this assumption that the second order closure will give the same result as the quasi-linear theory. And we see that, in fact, that assumption needs to be re-examined. That was certainly my thinking anyway. And it stymied progress on our generalized quasi-linear approximation that I want to tell you about. So,
question?
Yes.
Sorry.
Yeah.
What is the other bar? This, on the previous slide, please.
Oh.
Yeah, what's the other bar?
The over bar here
Yeah,
on the right-hand side.
yes.
So think of these, so it could be a horizontal average. In this case, it's just, there's not really any averaging in this simple example. But in the case, think of this as if we look at each value of the zonal wave number for our second cumulant, it's just a product of the fields at that zonal wave number. So, but at each zonal wave number m, we have this matrix that depends on L1 and L2, and that's the thing that has a rank that's different than 1.
Okay,
Yeah.
here is the product one, there's no...
Yeah, there's nothing fun. I'm just doing that by analogy, basically. Yeah. So this code you're welcome to run. It's, if you have a Mac, you can download it for free from the Mac App Store. It's called GCM. It does, we look at lots of different models on it. So this just summarizes the result. Here was the case of our weak forcing. You can see with your eye that the spectra between the comparing quasi-linear and C2 is identical. But then if we look at strong forcing, there is this difference where there was the wave excited at m equals 3 that's not present at m equals 3 for the second order cumulant expansion. Well, let's see how well this closure at second order works for some problems. So Steve told you about the busa annulus problem, so I'm not going to go through that in too much detail. These are the equations of motion. So we have a direction x, an inhomogeneous direction, and, or sorry, a direction y rather that's inhomogeneous, and a direction x going around the sphere, which is our zonal direction. And these are Hofmolar plots of the first cumulant. This is the velocity, and this is the temperature. And up until time t equals 2, we're running DNS, fully nonlinear simulation. And then we switch, using the initial conditions from the nonlinear simulation, we switch to the second order cumulant expansion. And you can see that it does pretty well qualitatively. It captures this single jet and the structure in the mean flow. However, if we look at the second cumulant, it now has a rank that is greater than 1. So this agreement between the numerical simulation and CE2 actually is best for initial conditions to CE2 that yield this higher rank solution. And it's just to say that it's not obvious what the best solution will be. It's not obvious that seeking a rank 1 solution, which is what quasi-linear simulations would give you, is necessarily the best solution. In this case, actually, it isn't. There are some initial conditions for our second order closure that have rank 1, and they do not reproduce this result. So we have two types of quasi-linear approximations, and we need to think carefully about the rank of our second cumulant. The second cumulant expansion is, this is a direct numerical simulation, again, of the same problem in a different parameter regime that's showing some weak bursting. You might be able to see it's a little bit faint here. And the second order cumulant expansion is actually able to reproduce this bursting, although in a much stronger way. And that's something that we usually don't see in other problems that have bursting. Usually the second order expansion isn't able to capture that. Now, going back to that Herring quote, I think he formulated this very carefully by not saying that the third cumulant is 0, but by saying simply that it's decoupled from the first and second cumulants. And what that means is that the statistics are not necessarily Gaussian. A Gaussian distribution would have only the first two cumulants non-zero. But in fact, for quasi-linear simulations, they typically aren't Gaussian, for at least if we use zonal averaging. And we explored that a while back, looking at a stochastically driven jet. This is a time evolution of the stress, basically the Reynolds forcing of the mean flow. And you can see that it's highly non-Gaussian with these rare events that have exponential instead of Gaussian type of tails. So there's some very interesting statistical information that's not captured by the second order approximation, but can be captured by looking at something called the Riccati equation, which is a generating functional for these, the tails of these distributions that we examined in this paper. Now, a critique of direct statistical simulation is that we're looking at these high dimensional objects. Even the second order cumulant would have a dimension of 6 before averaging, and then maybe it's reduced to, if we're looking at a three-dimensional problem, it'd be 2 times 3. Then if we average in, say, 2 directions, we still have a 4-dimensional object, which is expensive computationally. However, it appears that in many problems in this quasi-linear approximation, there's a very strong dimensional reduction. And so we've looked at the transition to turbulence in pipe flow in the quasi-linear approximation, in which the averaging operation is in the azimuthal direction around the pipe, yielding these kinds of mean flows. And comparing a nonlinear to quasi-linear approximation as a function of increasing Reynolds number, we can see here that we have these puffs of turbulence separated by rather quiescent regimes, and the same thing appears in the quasi-linear approximation. So the quasi-linear approximation is actually able to capture the transition to turbulence in pipe flow. But because its spectrum is so truncated, and we saw that in the live simulation I showed you, that means that the dimension of the quasi-linear simulation is much less. So this is a plot in the zonal direction of the power spectrum in the nonlinear simulation. In the quasi-linear simulation, you have basically a truncation to 0 beyond a few wave numbers. This was noticed by Rich Kurzweil a number of years ago, where he retained only the m=3 mode. He did a quasi-linear simulation and found these, that he could reproduce the transition to turbulence. So that suggests that we can greatly reduce the dimensionality of our second cumulant and still yield meaningful results. Now we applied this quasi-linear approach to some other problems of interest, such as the dry atmospheric boundary layer. This is comparing this is convection with a fixed flux at the surface. The nonlinear simulation with the quasi-linear simulation. You can see the quasi-linear simulation has waves that are much too coherent because of the neglect of the eddy-to-eddy scattering process. And actually, I think, just want to emphasize that the real import of the quasi-linear kind of thinking is not so much trying to get agreement in all cases with the full simulation, but increasing our understanding of the flow. And so actually, it's the cases where we get disagreement that we learn the most. And here we see that the quasi-linear simulation is able to show the deepening of the mixed layer on the boundary layer, where the potential temperature is basically constant as it evolves over time, perhaps as the sun rises and starts heating the surface. But when we look at fluxes, the second order statistics, the agreement is not so good. And Steve told us about a remedy to this problem, which is this GQL approximation, which I'm going to talk about in a moment. We've also applied this to the ocean mixed boundary layer. And subject to some shear, Langmuir turbulence, just as in the problem with the thermal wind that Steve talked about, that can have an effect of ameliorating the nonlinearities and give us somewhat better agreement, but not great, with the quasi-linear approximation. So it's clear that we would like to go beyond the quasi-linear approximation. There's a number of ways that we might imagine doing this. One is to go ahead and retain the third cumulant. So we'll retain the pain in the neck term, but treat it perturbatively. So now we have three turtles, because we have the third cumulant on top of the second, on top of the first. And this is a bit cumbersome numerically, but it can be done. And furthermore, we can make life a little bit easier by converting the prognostic equation for the second cumulant, its tendency, to a diagnostic equation, doing by introducing a time scale. This is similar to what's done in eddy-damped quasi-normal Markovian approximations for isotropic turbulence, but now it holds for anisotropic turbulence, and it appears to still be realizable. It's expensive computationally, but I'll show you some results at the end for the stochastically driven jet, showing that it actually can work quite well. Instead, I'd like to focus most of the remaining time on this generalized quasi-linear approximation, where we break down the triads into long wavelength pieces and short wavelength pieces, and retain only 3 of the total 6 such terms. Again, neglecting this high wave number eddy to eddy scattering, but still retaining some long wavelength eddy scattering. So Steve wrote down these equations for this generalized quasi-linear approximation, and we designed this approximation with the view of doing an exact closure of these equations, because they treat the high wave number modes only at a linear level, like in the quasi-linear approximation. So there exists an exact closure, and which we call the generalized quasi-linear expansion, generalized cumulant expansion, GCE2. But we only recently realized so we did this early on after we developed this generalized quasi-linear approximation, but I could not get the agreement between the quasi-linear approximation simulations, the generalized ones, and the GCE2. And I just could not understand for the life of me why these two didn't agree, because algebraically, they should be equivalent. I'm deriving the closure directly from the generalized quasi-linear equations. So it was only when we realized that there was this rank instability that we could reconcile the two calculations and see that we do get agreement when the rank of the second cumulant is 1, and don't get agreement otherwise. So now we have an understanding of what was going on, and we can proceed to use these second-order cumulant equations for various problems. So let's return to the Kolmogorov problem. This is now on the beta plane. So for weak Kolmogorov forcing, here's our spectrum in kx and ky space for the fully nonlinear problem, and you can see that there's power everywhere because of the eddy to eddy scattering. In the quasi-linear and CE2 approximations, there's only this band of power, which is exactly what we saw in the live demonstration. I've just rearranged the spectrum and flipped it 90 degrees. Here in the general quasi-linear approximation and the GCE2, we get exact agreement between the two spectra, and we can see that the rank of the second cumulant is equal to 1 in this case. And here we see that the mean flow, unlike in CE2, now allows for some fluctuations, some long wavelength fluctuations. But if we go to strong forcing, then we have a disagreement between quasi-linear and CE2, and also the generalized quasi-linear and generalized CE2 approximations. You can see that the power spectra are different, and then looking at the rank of this second cumulant, we see that it is now changed from 1. So now we have this understanding. We can apply this to richer systems. So where are we going with this? One problem of practical import that a number of us are interested in is trying to understand better the flow of air past wind turbines. And Greg Cheney is leading a project to apply some of these statistical methods to this very practical problem. So the world is moving in the direction of having these floating offshore wind turbines, and we need to know how to design these in this complex marine atmospheric boundary layer environment, subject to rocking from waves and so on. Norway is the only country that has these so far, and this is a diagram showing the scale of the Norwegian wind turbines. But they're planned, or actually already efforts are underway off the west coast of the United States, off of California, building these things. And to give you an idea of the scale of the size of these things, they not only cannot be built in the Bay Area because they can't fit underneath the Golden Gate Bridge, they're taller than the towers of the Golden Gate Bridge. So these are enormous objects that are sampling, they're passing through much of the atmospheric boundary layer. It's providing a really strong challenge, a modeling challenge to understand the flow. Yeah.
And how much power, or whatever units you want, does one of these produce?
Yeah, a lot. I don't remember the number off the top of my head. But, well, so suffice it to say that the power transmission infrastructure does not exist to support this. So that's one of the big problems. Will there be an underwater cable that goes from the Oregon border all the way down to the Bay Area? Yeah, that's something that's being envisioned. So there's enormous engineering challenges involved with this. But already a group has started to look at quasi-linear type approaches for modeling airflow past these kinds of wind turbines. So this group at Johns Hopkins University has been using something called a reduced nonlinear model, which is rather similar to the quasi-linear approach. Here we've done some early work, really our collaborator Jeff Oishi, looking at flow past a fixed obstacle, just in 2 dimensions. This is the quasi-linear approximation, this is the generalized quasi-linear approximation, retaining just 5 wave numbers, and here's a fully nonlinear simulation. And you can see that the generalized quasi-linear approximation for which we could do this closure, it does a pretty good job of describing this very idealized flow.
Can I just clarify that the modes are in the spanwise direction? Or is
it? The mean flow is in the I think in the streamwise direction, not the spanwise direction here.
Oh,
yeah.
Thanks.
Yeah. All right. Well, that was a lot of material. Let me try to summarize the results of this program. So we have these different levels of approximation of direct statistical simulation. And let's see how well they do by returning to the tried and true problem of the stochastically driven jet on a sphere. So if we look at the generation of a zonal jet, super rotating zonal jet, in a full nonlinear simulation here, where we're driving primarily the low latitudes. And we see that there is a counterflow that extends all the way up north and south. If we compare that to the quasi-linear approximation, we can see the deficiency of the quasi-linear approximation because the counterflow does not get up to the high latitudes due to that absence of the scattering by the eddy-eddy-to-eddy scattering. And the same thing is reflected in the second order closure. These 3 approximations now attempt to get around that limitation by either including more triadic diagrams in the generalized quasi-linear approximation and its closure, or by treating the eddy-eddy-to-eddy interaction not in a perturbative way. And you can see that they do a better job of reproducing the so-called truth of this problem. But I want to close with some speculative ideas that a number of us have been working on. We've been asking the question, can this direct statistical simulation approach be implemented on a quantum computer? So the idea is that if we have some nonlinear dynamical system that I can write in this form, where this velocity is some nonlinear might have some nonlinear dependence on x, but this form would also fit the Navier-Stokes equation. Then I can write down an equation for the probability distribution. This is simply the Fokker-Planck equation. And it's simply following the time evolution of the probability distribution using the fact that probability itself is a conserved quantity. The integral of the probability is conserved, so we can write a kind of diffusion equation for that probability. But this is a linear equation, whereas this is a nonlinear equation. So there must be some conservation of difficulty. I can't simply go from a nonlinear equation to a linear equation. And of course, that conservation of difficulty lies in the fact that this is a PDE, whereas this is an ODE. Or if we were looking at the Navier-Stokes equation, this would be a PDE, and this would be a functional PDE. So the dimension of this equation that we want to solve is vastly greater than the ordinary differential equation. But a quantum computer, its power derives from the fact that it has a Hilbert space that's vastly larger than the classical Hilbert space. So we can ask, can a quantum computer address this problem? And so what we can do is form a linear operator. Basically, the operator is acting on the right-hand side of the Fokker-Planck equation, and then form a Hamiltonian, that is a positive definite product of L and L dagger, and find the ground state of this Hamiltonian with a quantum computer. That should give us the steady state probability distribution. So we've actually done this with the IBM, one of the IBM quantum computers. So there's now a number of quantum computers that have rather limited capabilities. They're called noisy intermediate scale quantum computers. And if we apply this, this approach to a simple 1D nonlinear Ornstein-Uhlenbeck problem, then this is a comparison of the probability distribution from an exact solution that we can just write down by hand and our quantum computer. And you can see that this does a quite good job. Souza has been looking, André Souza has been looking at the Held-Suarez model and using some machine learning techniques to write the Fokker-Planck linear operator in a much reduced dimensional space. And so this are some snapshots of the Held-Suarez general circulation model. It's basically the dynamical core at the heart of climate models. And so what you're seeing is for example, here are the mid-latitude storm systems moving, and then the quiescent equator. So we can look at the probability distribution of different realizations here from either classical approach or a quantum approach, and we get some fairly reasonable agreement, but not great, because the quantum computer has noise and our algorithms are variational algorithms. So we've now transformed this problem into a variational problem. The variational algorithms still need to be better developed. So before you run out and spend your money investing in quantum computing, you should read this article. There's a lot of hype in this field because there are a lot of investments being made in quantum computing, but there are a lot of exaggerated claims. And I draw your attention to this sentence, yet to date, a simple task such as multiplying 3 by 5 is beyond the existing quantum hardware. So some skepticism is definitely in order. Things are changing rapidly, though, but there are some intrinsically difficult problems with expanding quantum computing to interesting problems. So I think that most likely its greatest value may be in serving as inspiration to develop new classical variational methods that could be applied to the sorts of direct statistical simulation methods I've discussed. Thank you.
Thank you very much. Time for a quick question.
I have 2 questions and a comment. The comment is the GCM simulations that you ran, they looked very nice and very neat. I would love to use them.
Okay.
The questions are the following. So one thing is that you showed a channel drag versus Reynolds number in the channel flow.
Yes.
Was that calculated using the linearized, generalized quasilinear model or from DNS?
Well, it was calculated for each simulation based on the actual velocities that each simulation produces. So, for example, the transition to turbulence doesn't necessarily occur at the same Reynolds number between the different simulations.
And that's one. And second is that if you kind of want to estimate the drag by it,
Yeah.
how good an estimate do we make?
That's a good question, and I don't know the answer to that, but I think my student may know the answer to it, but I don't remember.
Thank you.
Yeah.
Thank you. I'm just noticing there was a question online, but I think there isn't any more. So.
No, actually there is.
There is still. Okay, no, that's fine. Cesare, go ahead.
Hello, Brad.
The next speaker set up. Thank you.
Yes, that concerns the transition in pipe flows. I actually wanted to ask whether you know if the quasi-linear approximation gives you back main field exponents for this transition, and if so, whether you know what does it take to get the correct percolation.
What does it take to get what?
Correct the percolation.
Okay. The exponents appear to be consistent with the fully nonlinear simulation, and we're working on whether the directed percolation picture can emerge from the quasi-linear simulation.
Okay, thank you.
Okay, thank you very much. So our next speaker